I'm gonna today I'm gonna present my work as a joint work on options and volatility. So I'm very thankful to the financial support from Stanford Bernstein Center. So let me start with some motivations. Consider a European option that is given to you. A very basic question is the price of this option increasing with volatility or not? So we all know from finance classes that if you have a conventional European call option, the answer is yes. But if you have another very simple structure like a binary call option, the answer is no. And that's a bit contrary to common intuition. So people usually think that if you have a binary option, then increasing volatility will result to a higher probability of ending in the money, so you will have an increasing price with volatility, but that's not true. Also, another related strand of literature in finance is about the managerial compensation. So managers can affect the firm's performance. They can gain expected return and volatility. If I want to summarize the executive compensation theories, there are two main pillars. The ancient and the older view is rent extraction view, which is the managers can choose their compensation to maximize their rents. But the more modern view is shareholder view, which is the board of directors, they can design some compensation scheme so that they incentivize the manager. So the two main questions that I'm trying to answer in this research is, first of all, what is the effect of volatility on option prices, European, American, real options? And the second one is try to incorporate those insights to a managerial compensation framework. So Edmonds and Gabay have an interesting survey of managerial compensation that they emphasize that this work hasn't been done that much, that if a manager can change the risk and return at the same time, then what would be the optimal compensation? So there is an early work done by Green in 1984, which he notes a notion of a concavified call. So where you have a call option and then you concavify the tail of the option, and then he uses a notion of warrants that leads to these sort of options. So I'm gonna build on these literature. So I have a theorem. Suppose you have a very arbitrary option given to you. The payoff of your option is a sum of some coefficients times some conventional European call. So it's a finite combination of calls. So the question is the price of this claim increasing with sigma when sigma is sufficiently high, or it's not increasing? And the answer is, if you look at this expression, the sum of alpha I times the square root of ki, so it's the determinants of this behavior. For example, here I have a graph of different concavified calls. From top to bottom, the degree of concavification changes. So you see that in the yellow curve, the option price is starting to be non-increasing with volatility. And if the degree of concavification is more, you see that the price is very non-increasing. So it increases and it decreases to zero. So and then I do this exercise for Arrow-Debreu prices. So Arrow-Debreu price is a claim on a particular given state of the world. So if, for example, Apple's stock is 200, how much are you gonna pay if I pay you $1 if Apple stock is exactly equal to 200? So these Arrow-Debreu prices are also behaving non-monotonically with volatility. So for example, if you take one particular Arrow-Debreu price and plot it against the volatility, you see that it first increases and then it decreases. So let me put all of these in a very simple model of managerial compensation. So suppose you have a value the firm's value given to you by this exogenous expression. So beta times the mu minus alpha times the deviation from an optimal sigma. So sigma star here is the value that is maximizing the firm's value. So we want to ideally induce the manager to choose sigma star. If you give the managers a call option, then the manager would choose sigma equal to infinity, and you will not get the maximized value for the firm. But you can optimally implement the optimal contract using a concavified call with a proper degree of concavification. So that's a very basic insight, that concavification helps you to induce the manager to choose the optimal level of volatility. So the ongoing work here is that how to write this in a formalized model of managerial compensation, and how to look at the effect of volatility on other class of option prices. Thank you so much.
Okay, so you have one question that came in through the chat box. How realistic are the parameters to the option will lead to an inverse relation in volatility and price?
Sorry, let me bring the, can you say again?
Yeah, how realistic are the parameters to the option? How realistic is it that the parameters to the option will lead to an inverse relation in volatility and price?
How realistic that the parameters to the option will lead to an inverse relation in volatility and price? I don't understand the question. How realistic?
Professor Kuga, do you want to go off mute? We have about a minute.
So we did it pretty quickly. So forgive me. You had a figure which showed that most of the for the stylized simulations, or however you drew those lines for them, that when the price was at one, if that was your purple one below, you had a green one there, which alpha, I think was alpha is your parameter there.
Yeah. So
alpha is less than 0. So how realistic that you will find that to be the sort of contract that should be written on a compensation?
So this value of A is realistic. I mean, if A is equal to half, it means you have a call, but you concavify it half the way through a flat line. So and then if your question is what are the range of the sigmas that are realistic, so the range of the sigmas that are realistic is from 0 to half, for example, and then it doesn't matter, because if you change the parameters of this concavified call, you can capture any value of sigma star. So I haven't put that theorem here. So the theorem is that if you change the parameters of this concavified call, you can pin down any value of sigma star that you want. So it doesn't matter, it's 0.1 or 1 or anything. Great, thank you.